Welcome to This Explainer. Today, we're going to explore how the universe perfectly balances its energetic checkbook. It's actually a really fascinating concept when you stop and think about it. Have you ever wondered why a roller coaster can only go so high after a massive drop? Or why a swinging pendulum eventually always has to come back down? Well, it all comes down to this strict cosmic accounting system where absolutely nothing is ever lost and nothing is ever gained for free. We're going to unpack the science that proves this elegant reality. So listen to this fundamental rule of nature. Energy can neither be created nor can it be destroyed. It only changes from one form to another. This reveals that the sum of all forms of energy in the universe always, strictly remains constant. You can't just make energy out of thin air, and you definitely can't just delete it. It's kind of like pouring water between different shaped glasses, right? The shape of the water changes, but the total amount of water, exactly the same. We're going to dive into the math and the physical models that prove this is happening all around us every single second. Okay, here is a quick look at our roadmap. We've got 5 sections today, starting with the universal law of energy, then the anatomy of a free fall, the energy ledger, the simple pendulum, and finally, calculating the real world. Section 1, the universal law of energy. 2 sides of the same coin. Let's get right into it. To really understand this, we need to meet the 2 primary forms of mechanical energy that are constantly trading places. Think of mechanical energy as the overarching currency, and it comes in 2 distinct denominations. First up is potential energy, which we call U, and that equals mass times gravity times height. Basically, this is the energy of position. If you hold an apple high up in the air, it has a lot of potential energy simply because, well, it has the potential to fall. On the flip side, we have kinetic energy, or K, which equals 1/2 mass times velocity squared. This is the energy of motion. In a perfect world, without friction, these 2 act exactly like trading currencies. When one goes down, the other goes up by the exact same amount. If you drop that apple, its height decreases, meaning its potential energy drops. But it speeds up as it falls, right? So its kinetic energy rises perfectly in sync. Moving on to Section 2, Anatomy of a Free Fall, proving the constant. It's one thing to say they trade places, but it's way more satisfying to see the absolute precision of the math. Let's mathematically prove this constant exchange by tracking a freely falling body dropped from a specific height. Imagine 3 distinct checkpoints for a falling mass. Position A is right up at the top, the moment right before the drop. Position B is an arbitrary point mid-fall, where the object has dropped a certain distance. And position C is the exact instant the object hits the ground. We're going to audit the energy at each of these 3 stops. If we calculate the sum of kinetic and potential energy at each point, the dense math simplifies beautifully. At the starting line, position A, the object isn't moving yet, so kinetic energy is strictly 0. All the energy is potential, mgh. Now, mid-fall at position B, it's lost some height but gained speed. The kinetic energy becomes mgx, and the potential is mg times h minus x. Add those together, and the x's literally just cancel out entirely. You're left with exactly mgh. And finally, at position C, it has no height left, so potential is 0, but it's moving at absolute maximum speed. The kinetic energy maxes out at exactly mgh. So the total energy is precisely mgh at every single step of the fall. The universe's ledger never changed. Section 3, the energy ledger, upward and downward motion. Let's map out exactly what happens at specific heights, whether an object is falling down or being thrown straight up. The really crucial point happens right in the middle, at exactly half the height. This is where the total energy is perfectly split down the middle. You have exactly 50% kinetic energy and 50% potential energy. At the very top, it's all potential. At the very bottom, it's all kinetic. But right there in the middle, the 2 energies meet in perfect equilibrium. It underscores just how incredibly linear this trade-off is. If you were to graph this out, you wouldn't even need to read the numbers to understand the relationship. Picture the kinetic energy steadily rising exactly as the potential energy falls. They form a perfect X right there in the middle. They cross precisely at half the height and exactly at half the energy. And the best part? The line representing the total energy sits flat right across the top. It never goes up, it never goes down. Just a solid, flat line. It is the ultimate visual proof of conservation. Section 4, the simple pendulum, energy in full swing. Let's move away from freely falling objects for a second and apply this exact same principle to something slightly more dynamic, a swinging simple pendulum. Now, you might think swinging back and forth complicates things, but the universe applies its ledger here just as strictly. Think about a pendulum bob's resting position at the very bottom and then its extreme raised positions on either side. When you pull that bob to the side and let go, you are doing exactly what you did when you lifted the apple earlier. You're giving it height, you are giving it potential energy. And here is how that builds a continuous cycle. At those extreme edges of the swing, the pendulum bob actually stops moving for a microscopic fraction of a second before reversing direction. Because its velocity hits zero, its kinetic energy hits zero. At that split second, it is entirely potential energy. Then, as it sweeps down to the center position, it loses that height but gains maximum speed. So at the very bottom of the arc, the potential energy drops to zero and it becomes 100% kinetic energy. It creates this endless, perfectly balanced swing. All potential at the edges, all kinetic at the bottom, and a perfect, constantly shifting mix everywhere in between. Section 5. Calculating the real world, putting it to the test. We have the theory and we have the concepts, but physics isn't just theory, right? It's practically applied math. So let's finally lock this in with a real numerical calculation. Imagine we have a small 50-gram ball, and we throw it straight up into the air with an initial speed of 20 meters per second. First, we figure out our starting currency. We use our kinetic energy formula, crunch the numbers, and we find that we've given the ball exactly 10 joules of initial kinetic energy. Now, assuming negligible air friction, the conservation law tells us exactly what will happen next. All 10 of those joules must be perfectly converted into potential energy at its absolute highest point where it momentarily stops before falling back down. Because we know for a fact that the potential energy at the top must equal the 10 joules of kinetic energy at the bottom, setting up our equation is a breeze. By plugging our known numbers into the MGH formula, we seamlessly solve for the height. And the math spits out a maximum height of exactly 20 meters. That is the true beauty of this entire concept. Without getting out a tape measure, without doing a single physical test, the law of conservation of energy lets us predict the physical world with absolute unwavering precision. But here's a thought to leave you with. All of our calculations today strictly assumed a perfect vacuum. But in reality, we don't live in a vacuum. If you throw that 50-gram ball 20 meters into the air resistance is going to push back against it. The ball actually won't quite reach 20 meters. But wait, didn't we say energy can never be destroyed? We did. In the real world, air friction forces the moving object to do work against it, changing a portion of that beautiful kinetic energy into heat energy, which just dissipates into the surrounding air. The energy isn't gone. The universe's ledger is still perfectly balanced, it's just that the currency got converted into a form we can't easily get back or use. It forces us to ask, how else is the universe constantly balancing the ledger around you right now in ways you can't even see? Thanks for joining me on this explainer, and keep questioning the mechanics of the world around you.